So as we're looking here on this electric field part 2, I have on this sheet of paper I have on here the workout that I'm going to have for this number 3. So I try to draw out the scenario, and we see that we have this electric field. It's pointing to the right. That shows the direction that this positive charge would go. A positive charge would go this way. Therefore, when we see this going the other way, this has to be a negative. So that's why the answer for A is negative. And then I ask, well, what is the force on that charge? Well, we have this equation that force is equal to that electric field times the charge. Where'd I get that? From my equation sheet. I have it written out. I'm not making up stuff. I'm using what I got to my advantage. I'm taking this electric field times the charge. That microcoulomb, the micro stands for times 10 to the negative 6. So we need to say what this is. So I put up on top of this E, this little arrow. That's saying that that electric field is a vector. It's saying it has a direction. So this force, I'm also going to put an arrow on top of it because it's a vector. So this force is a vector. That's why it's this much, 6 to the left. 6 times 10 to the negative 4 newtons to the left. So this is what we got here for this number 3. Now for you, what you need to have for you is just this part. That's all you had to have. I'm drawing it out because drawing and writing actually helps learning. That's why teachers do it. We don't like to just torture you. We do enjoy that. That's actually the number one list of why new teachers get into teaching is the torture. So we have the force on that charge. So now I'm going to take us to number 4. So on this number 4, we're going to be dealing with a positive 2 microcoulomb charge moving, or it's going to be placed in this electric field. And we see that this electric field, once again, is going to the right, and that shows the direction that a positive charge would go. So I see this electric field. I put the little arrow on top of the E because it is a vector. So this positive charge would go to the right. And we have this positive 2 microcoulomb charge. So it says some things in letter A and B. And then letter C is talking about the force. Letter D asks us about this acceleration. And this letter E is saying, well, how fast is it going? And so I put the arrow on top for the force because it's asking for, well, how much and which way? How much, which way? And same thing with velocity, how much and which way? We should already be able to tell that this is going to be moving to the right. So getting back to document. So in talking about the motion for this, we have an idea that this charge is going to start from rest and accelerate to the right. So we kind of know that it's starting here from rest, and that's what it says here, given, and it's going to accelerate to the right. So in terms of the motion, that's what we got going on. But now we can talk about the energy. The energy is stored in this electrical field. Just like if I were to drop a ball on someone's head, gravity would pull it down. The gravitational field stores that energy. But here, we're storing it in this electrical field. The electrical potential energy is transformed into kinetic energy. That's just what it is in terms of energy speak. So then getting down to this C, D, and E. Well, for this letter C, it's asking us to find this force, which is going to be this Q times E. Q is the 2 microcoulombs. The electrical field is 400 newtons per coulomb to the right. So we get our 8 times 10 to the negative 4 newtons, and the direction of it is to the right. Then getting down here for letter D, if we know that's the net force acting on this charge, we can say that there's no gravity. We're not talking about anything there. Or we could talk about just the net force in this X direction. But really, the only force that we're concerned with right now, the net force, which is mass times acceleration, equals to this QE. We figured out what the force is. So now we can solve for the acceleration. We know how much mass there is. it was 0.1 grams, which is 1 times 10 to the negative 4 kilograms. We have to use SI units. A Newton per kilogram is the same as meters per second squared. So that's how we get this 8 meters per second squared. And we know the direction of it. The direction of it is to the right. Lastly, for this number 4, it's asking us to find not just the direction of it, but how fast is this going? If we know the force making it move to the right, and we know it's accelerating going to the right, it's going 8 meters per second every second. That means 1 second later, it's going 8 meters per second. In 2 seconds, it's going 16 meters per second. In 3 seconds, I'm not going to do that math. But what I am going to do is show us that, well, there's 2 different methods we can use to solve this. So this is getting back to what we did way back in like November. So we could use this x equal to 1/2 at squared plus v naught times t plus x naught, where it starts from rest. So there's a 0 velocity, and we're talking about how far it goes. Well, we know that acceleration. If we know the acceleration, we can find the time because we're trying to see, well, after 1 meter. So we know x. And you find the time. Then you could use this right here. Once you know the time, you plug in t into here, because this is also 0. And then that gets you to the velocity. Or there's a combined equation as well. And this is the one I'm using, because this v squared that I'm looking for, the velocity, is equal to this 2ax plus how fast it started squared. Well, v naught is 0. So this is what we're left with. The velocity squared is equal to 2ax. So I square root it. We found a as this 8 meters per second. The position is going to change by 1 meter. Therefore, our velocity is going to be 4 meters per second going to the right. All right, so then lastly, we're going to get down to here. So this diagram is going to show this negatively charged oil drop, and it's going to be suspended here amongst this. So we got a positive plate, negative plate, and other stuff going on. Really, what we're doing is the Milkian oil drop experiment. So this is a famous experiment, and what it did was it found what the charge is for 1 electron. So I told you at one point that it's 1.602 times 10 to the negative 19 coulombs. And we found out because of this experiment. And what we have is we have this oil drop on here that has negative charges in it. It's negatively charged. And we have an electric field that makes this negative charge go up, and this gravitational field that makes the mass go down. So we have then the forces, gravity down and electrostatic force up. They're going to be equal and opposite to one another. So what we're seeing is this oil drop just kind of floats in space. And it floats because the force up equals force down. So we're asking here, based on the givens, what is that force down? Because if we know the force down, then we know the force up. And then from that force down, what is the charge on that oil drop? We know the force down is due to gravity. So it's mass times the gravitational field. The mass is given at 1.96. Gravitational field, 9.81. That is the acceleration due to gravity. That is the gravitational field strength. If there's something you guys walk away from this class is, please know that this gravitational field strength is this 9.81. It's that G. The G down the street never changes. So this force due to gravity, then, we know this force in terms of newtons now, and it's down. So we have the direction as well, that it's going down. In this letter B, now we're trying to find out this charge Q. Well, we know the sum of the forces is equal to 0. If we were to add all the forces on it, it's not moving. Therefore, that's what these 3 dots mean. It means, therefore, we know that mass times the gravitational field is equal to charge times the electrical field. Solving for charge, Q, it gives us this expression. With the gravitational field divided by this electrical field, the vector notation cancels out, leaving us just with the scalar here of the charge. So we get this value of this negative 4.8 times 10 to the negative 19. I know there's no negative here. I know there's no negative here. My electrical field is pointing down. So a positive charge would go down. But what we're seeing is this negative charge is getting held up. So that's how I know the charge has to be negative. So I know this charge is this negative 4.8 times 10 to the negative 19 coulombs. Now, this is all I'm asking, but I'm going to take it another step farther, saying, well, the number of electrons is really the whole point of this experiment. They wanted to see how many electrons are on this oil drop, and then what is the charge of one single electron. So you could take this Q divided by this elemental charge, the 1.602 times 10 to the negative 19, and we see that we get about 3 electrons that were excess on that. Now, that doesn't mean that we're only 3 electrons on that. It means that there's like 1 billion protons and 1 billion and 3 electrons. The net charge is what we're concerned with. So, leaving us with what we had here. So I am going to take us back over to our course. Note that our next week is this Unit 4 potential. On Monday, I want you getting all your fins on your rocket. Next week, we are working on this potential. Next Friday, we do have a test. It's going to be a test on charge, electric field, and potential. So on Monday, I want you to make sure you get your fins all on. So I put up here some videos of how to inspect your fins because, well, you can't get me some bad fins. Don't put on more fins if you did the first one bad. Check out your fins. So I show you in here how to put your fins on, how to attach them, and how to inspect them. Because I want you to inspect your fins before you do anything, before we launch. Inspect the second fin as well, and glue on the third. Then I ask us this question. This is the way I'm taking attendance. Were you in school on Monday? Do you have all 3 of your fins on? I have all 3 of my fins on. I'm working on my essay. My fins are not on, but I'm aware of the deadline. The deadline is when we were launching the rocket. All right.